In this next section, we are going to do some things similar to what we did in the last section, but just a little different. So in this section, we're going to talk about constrained max and minima problems. Most of these are going to be word problems, but not all of them. So just like in the last section, you're going to get some problems where you're given the equation and asked to find the extreme values and go through the process and solve. But there's also going to be some where you're going to have to come up with the equations and do the process as well. Now, the constrained max and minima problems are, like I said, a little different. The idea is still the same. Given a function, we want to maximize or minimize this, but the difference now is our function may have some constraints on it. Okay? And so to talk about this method, which is the method of Lagrange multipliers, I'm going to do a specific example, and then I'll lay out the steps and talk about the Lagrange multipliers as I go. Okay? So, like I said, constrained maximum and minima problems are to find the extreme values of functions of several variables that have some constraint by some criteria. All right. So suppose we have a cost function for a certain product given in this fashion: c of xy equaling 2x squared plus xy plus y squared plus 200, where x is the number of units manufactured at one plant and y is the number of units manufactured at another plant. And we have an order for 200 units that we want to make, and we want to minimize the cost for this function. Okay? Alright, so here, the first thing you're going to want to do for any of these problems is start by figuring out what your function is and what your constraints are. Okay, and usually what we're going to do is we're going to call f of our variables, and these do not necessarily have to be two variable functions. So this is one difference from the extreme values where we used our Hessian and extreme values that we can use Lagrange on. For Hessians, we had to only have two variables because that h that we found was defined only for second order partials of two variable functions. So if I have more variables, I can't use my Hessian. I can always use Lagrange. Lagrange will work for any 2 variable, 3 variable, 4 variable, etc. functions. Okay? So here I'm going to start by defining my f of xy. This is the function we want to maximize or minimize. So in this case it's going to be the 2x squared plus xy plus y squared plus 200. And if you want to leave it called c, you can. In this case I'm going to call them f and g just so that you can set these up in the future. This is my objective function. And here I do mean it as a function, okay? It's got to be written as some f of xy equaling some expression. Okay? I'm going to call g of xy. It's also going to be a function of my 2 variables, but this is what we're going to call our constraint equation. So g of xy in this case is the fact that we want to have 200 units made. And it doesn't matter which plant, but we know the sum of the 2 plants together have to give us the 200 units. So here, x plus y has to equal 200. Okay? Our constraint equation is the one, and again, first off, it's an equation, but we want to be able to rewrite it as a function. I'm going to call it that g of xy. So here, my g of xy, I'm just going to say is x plus y minus 200. Okay? Once I have those 2 things, then I can set up our Lagrange. And our Lagrange is basically an equation that's going to relate our function with our constraint. And we're going to form one function between the 2 of them so that when I optimize that Lagrange function, it actually maximizes or minimizes my f based on the constraints given in G. Okay? And so here I want to form, I guess I don't want to call it let's form a Lagrange equation. And this is always going to be found by taking f of our function, whether it's two variables or more, minus some variable. I'm going to use lambda because that's how it's usually defined. Lambda is just a Greek variable. If you want to use w or k or u or whatever, you can. This is going to be lambda times our g of xy. Okay? So here, our Lagrange equation, and we're just going to call this L of xy lambda. So our L of xy lambda for this particular function is going to look like 2x squared plus xy plus y squared plus 200 minus lambda times g. So lambda x minus lambda y plus 200 lambda. Okay, and some people don't like the lambda because it looks like 2's. That's why I said you can use any variable you like. Okay, once I have my Lagrange equation, here's where our partial derivatives come in. Okay, so very similarly to how we started our Hessian is, I'm going to take my first order partials. So I'm going to take my first order partials of L. And again, mostly I'm doing this because I need my critical points. Okay? Now, the difference between what we did with the Hessian and this is here, when I find my critical points, these critical points satisfy our function f, but are also satisfied by our g. And so the nice thing about this is it gives me my optimized solution without having to do something extra. Okay? So here I'm going to go ahead and take my first order partials. So in this case it's a 3 variables, so I'm going to need to take all 3 variables. So I'm going to want L sub x, I'm going to want L sub y, and I'm going to want L sub lambda. Okay, so looking at this equation here, L sub x, again treat everything not x as a constant. So I'm going to get a 4x plus y, that goes to 0, that'll go to 0, minus lambda, and those two terms will go to 0. For L sub y, that goes to 0, I'll get an x plus 2y, that'll go to 0, that'll go to 0, minus lambda, and then that one will go to 0. And then lastly, for L sub lambda, we'll get all of these going to 0. We'll get a minus x minus y plus 200. Okay? So now I just need to take these first order partials and find my critical points. So I'm going to find critical points by solving Lx, Ly, L lambda, all equal to 0. And then whatever I get out of there, that is going to be my solution that gives me my optimized values. Okay? So looking at this system, this says that 4x plus y minus lambda equals 0, x plus 2y minus lambda equals 0, and minus x minus y plus 200 equals 0. That's the system I want to solve. Now, most of these equations that you're going to have are going to be similar to this, where I have 2 of my variables and my lambda in my equations. And the nice thing about it is if I don't have powers, meaning I'm looking at a linear system, I can actually solve this like a linear system. So all I'm going to do here is I'm going to take and I'm going to solve these 2 equations. I'm going to eliminate the lambda, and then I'm going to have 2 equations, the one from these 2 plus this one, that are in terms of x and y and some constants. So here I'm going to take the first equation minus the second equation, so 4x plus y minus lambda equaling 0, and x plus 2y minus lambda equaling 0, and I'm going to subtract these. Okay, so I'll get a 3x minus y, the lambdas go away, equaling 0. Okay, and from my last equation there, so 3x minus y equaling 0, and minus x minus y equaling negative 200. Again, if I subtract there, I can see that I'm going to get 4x, the y's will cancel out, equals 200, so x will have to equal 50. Okay. Once I have the x, I can plug back in to get my y. So I know that 3 times 50 minus y equals 0, so 150 is equal to y. And I can solve for my lambda. Now we don't really need lambda because lambda was just the multiplier so that I can get my constraints into my function. But you can also solve for that. In some cases, especially in WebAssign, you may be asked to actually find lambda. And again, I can just plug back in to solve for lambda. So 4 times the 50 plus the 150 minus lambda equals 0. So it looks like 200 plus 150, or 350, is equal to lambda. So my solution here, the x and y are the only things I really need. Coming back over here to our problem, it says that if I'm looking at this, I need my x, which is 50 units from the first plant, and my y, which was 150 units from the second plant. Will minimize my costs. Okay, and this right here is your last step of the problem. So this is number 5. This is where I'm going to state my solution. In some cases, it's just rewording what we just found. In some cases, I may have to plug in. So if they ask for the minimum cost, I'm going to plug back in here with these values and figure out what my minimum C is. But there's my Lagrange. Okay. We can look at a couple more examples of these. They all are going to work the same way. The only difference is how your constraint plays into your function and then how to go about solving that system of equations. Okay, so in this next example, we're going to do the same thing. We're going to set up a Lagrange equation so that we can find the optimal solution for the problem. So here we have a production function, f of the Lk, equaling 12L plus 20K minus L squared minus 2K squared. The cost to the firm is $4,000 per unit of L and $8,000 per unit of K. If the firm wants a total cost to be $88,000, we want to find the greatest output possible based on the budget constraint. Okay? So here, we're going to start by setting up our functions. We're going to let f again be our function we want to optimize. And our g is going to be our constraint. So here we can see if we take 4,000 L plus 8,000 K, that has to be at most 88,000. And you'll notice there the thousands, I can kind of get rid of those extra zeros all the way through the equation. So here I'm going to say 4L plus 8K minus my 88. There's my constraint. So again, if we think of this as an equation, 4L plus 8K has to equal 88. So when I subtract the 88, there's my function. Okay? So this is going to give me my Lagrange equation. So my capital L of L, K, And again, if you don't like lambda, pick some other letter. So LKX is going to look like 12L plus 20K minus L squared minus 2K squared minus 4LX minus 8LKX plus 88X. Okay, so there's my Lagrange equation. Okay, from there I need my derivatives. So L sub L is going to look like 12 minus 2L minus 4X. L sub K is going to look like 20 minus 4K minus 8X. And L sub X is going to look like minus 4L minus 8K plus 88. Okay. Now, using those, I'm going to set up my system and solve. Okay. So my system here, 12 minus 2L minus 4X equaling 0, 20 minus 4K minus 8X equaling 0, and negative 4L minus 8K plus 88 equal to 0. Okay. Now this one's a little different than the last one because if I look at each of the first two equations, I only have two of the variables in there. And one variable is the same in both of them. So here I can actually rewrite and then use that last equation, in other words, use a substitution method to solve. So that first equation I can think of as 2L will equal 12 minus 4X, or L will equal 6 minus 2X. And then I can do the same thing with the second equation. So 20, so if I solve for K, 4K will equal 20 minus 8X, or K will equal 5 minus 2X. Okay? So now, using those two and substituting this into the last equation, I can see that 88 is going to equal 4 times 6 minus 2X plus 8 times 5 minus 2X. Now I have one equation with one variable, so I can just solve for x. So here 88 is going to equal 24 minus 8x plus 40 minus 16x, which looks like 64 minus 24x. Subtracting, so 8 minus 4 looks like 24 will equal a negative 24x, or x will equal negative 1. Okay. Should be almost hesitant that you're getting a negative there, but remember x is our Lagrange multiplier, so it's okay for that to be negative, as long as our L and K don't come out negative. So now we can plug back in L, 6 minus 2 times a negative 1, we can see is 6 plus 2, or 8. And then K, equaling 5 minus 2 times negative 1, which is 5 plus 2, or 7. And so both of those are coming out positive, which is good. That's what we want. Okay? So to answer our question, we want to find the greatest output possible based on the budget constraints. So we know how many units of each we want. This says that 8 units of L and 7 units of K will give the max output. But that doesn't tell us what the maximum output is. So to get that, we actually need to plug back into our function. So f of 8, 7 is going to look like 96 plus 140 minus 64 minus 2 times 49. We just need to simplify that. So that looks like 236 minus 64 minus 98. So 236 minus a 162, or our max output is going to be 74. And they don't really tell us what this is, but it's a production, so this is just our max output of 74. And that will keep us within our budget constraint of $88,000, okay, using the numbers that we know for L and K. Okay. So again, the idea behind these Lagrange multipliers is I don't have these extra tests I have to do. I don't have a first derivative or a second derivative test to get my optimized solution. I can just use the fact that I can use the constraint along with the original equation and get the critical values there, and it will optimize that equation that I want based on that constraint.